Hi everyone, welcome back. Today we're going to talk about the Milky Way, the galaxy what we call home. So, on a clear night, if you're in a very dark area, you'll see a kind of milky band stretching across the sky. But this had been known since ancient times. In fact, the name Milky Way galaxy is actually a bit of redundancy because galaxy, from galactose, that the sugar, one of the sugars in milk, this reminded people of kind of spilled milk spread across the sky. But in 1610, Galileo used a telescope that he had built to view this band, and he found it was composed of countless individual stars. So here's a nice time exposure of this. And notice that you also see these dark areas in here as well. What the nature of these dark areas had mystified astronomers for quite a long time until we figured it out during the 20th century. So that band of light is the combined light of hundreds of billions of stars that are far too far away to be seen with the unaided eye. And for that matter, every individual star that you see with the unaided eye is part of the Milky Way galaxy. Now, there are occasional exceptions to this, the most notable of which was in the year 1987, when a star exploded in the Large Magellanic Cloud, a supernova, and that was visible to the unaided eye. It peaked at a apparent magnitude of about 2.8 or 2.9, and it was visible for a while before it faded from view. So our galaxy, since we're kind of in it and it actually has a disk-like structure, makes it hard for us to figure out exactly what its composition is. We didn't really work this out fairly well until starting around the 1950s with the help of radio telescopes. In fact, it wasn't even until the 1950s that we even realized that we lived in a spiral galaxy. So here's our nearest large neighbor, the Andromeda Galaxy. M31 that is, and you can also see two of its companions, M110 up here and M32 down here. And if you zoom into the Andromeda Galaxy, you see countless individual stars, just as Galileo saw with his telescope pointed at the Milky Way sky. And here's another nice spiral galaxy, NGC 4414. And another really nice one, a so-called Grand Design Spiral, the Whirlpool Galaxy M51. And here's another nice one as well. Now, we live, again, in the actual disk of the galaxy. So our view is actually kind of similar to the view that we have of this edge-on spiral galaxy, NGC 4013. And this thing right here is not a supernova explosion. This just happens to be a foreground star of the Milky Way. Now, in 1785, Sir William Herschel used a telescope to map a number of different regions of the sky, 683 in fact, and he counted the number of stars he could see in each of those regions. And upon doing so, he created a map of the Milky Way, where, surprise, surprise, our sun is at the center. This was kind of going back to this idea that, yeah, we're maybe in a special place of the universe. It's a little bit of a violation of the Copernican principle. Copernicus had reworked out the fact that Earth and the other planets are going around the sun, with the sun being relatively motionless, at least from our point of view. And still, though, Herschel and a lot of astronomers around his time figured that our sun, nonetheless, our solar system, that is, as a result, is basically at the center of this place that we call the Milky Way. Now, the reason he came to this conclusion is because of the effect of dust. Astronomers didn't understand dust back then, but dust limited his view to a distance of 6,000 light years. So if you're in the middle of a desert and it's very foggy, and the fog is limiting your view to, say, 200 feet in each direction, your whole world is basically going to be symmetrical out to a distance of 200 feet. And beyond that, you don't have any knowledge. This is analogous to what was limiting astronomers like Sir William Herschel. In fact, this was used until the early part of the 20th century. It was at that point when Harlow Shapley, about whom we're going to say more in another lecture, figured out that we are definitely not at the center. What he did is he was able to determine the approximate distances to globular clusters using RR Lyrae stars. RR Lyrae stars are a type of variable star that can serve as a standard candle. They're not as bright as Cepheid variables, so you're not going to be able to use them to determine the distance to the center of the Virgo cluster or anything like that. But they're still bright enough to be able to map clusters in the region around our Milky Way galaxy. So based on this mapping of globular clusters, which have lots of these RR Lyrae stars, globular clusters like this, Shapley was able to make a three-dimensional plot. And he originally figured that the galaxy was about 300,000 light years wide or so, which is big. And a lot of that is because of the fact that he was not taking into account the effect of dust. It's kind of an irony here. Dust limited Sir William Herschel's perspective to about 6,000 light years in each direction. In the case of Shapley, his inability to take into account the effects of dust meant that he overestimated the distances to these standard candles. In other words, these RR Lyrae stars, one of the main reason they looked dim is because they're far away. But another reason that they look dim is because there's intervening dust between us and the stars, and they didn't have the means of taking into account the effects of that dust at the time that Shapley was making his observations in the 19-teens. Nowadays, this is easy to determine. You're going to have a divergence from a black body spectrum. We call it an infrared excess, and based on the amount of infrared excess you have, you can make a magnitude correction on your distance estimate. But this is the plot that Shapley made of the Milky Way's globular clusters. The general three-dimensional appearance of these, which here is projected in 2 dimensions, is still correct. It's just that you need to put them a bit closer than where he actually plotted them. So here is a nice view toward the center of our galaxy. This is taken from the 2-micron all-sky survey. And even with, so 2 micron means that we're looking at a wavelength of 2 microns, that is 2,000 nanometers. That's in the near infrared part of the spectrum. And even though infrared light is often able to get through dust particles because of the fact that the wavelength of infrared light tends to be similar to or longer than the size of a dust particle, toward the center of our galaxy, there is so much dust and so much complex dust that even at 2 microns, you're still seeing a lot of this dust. When, if you were to look, say, in radio, you'd be able to see right through. So this is a more visible picture, and you see lots of these dark areas. These dark areas are dust. The dust was created from supernova explosions as well as the late stages of the lives of sun-like stars during their asymptotic giant branches as they are shedding off their outer layers. We now realize, though, that our Milky Way is actually what we call a barred spiral galaxy. It's a very thin galaxy. By that we mean that the whole thing is about 120,000 light years wide, but it's only about 1,000 light years thick. So we're talking about a ratio of 120 to 1 width to thickness. Our Sun is about 27,000 light years from the center of the galaxy, and it's about 70 light years above the center of the plane. And it's in the process actually of moving away from the center of the plane. Over millions of years, it oscillates back and forth, going through and away from the center of the plane in something resembling sinusoidal motion. But I should also mention that this 27,000 light year estimate, it might be a hair high. Some of the early results from the Gaia spacecraft surveys seem to be revealing that our distance might be a little closer to 26,000 light years, but we're going to be getting better estimates on this in the early 2020s as the Gaia spacecraft have more data releases and these end up being analyzed in much more detail. Here is our present-day view of the Milky Way. So here we have, this is in what we call galactic coordinates, but there's our Sun, and notice you have 2 really bright arms. You have the Scutum-Centaurus arm and you have the Perseus arm. And you also have a couple of dimmer arms, the Sagittarius arm and something called the outer arm. And newer researchers, a lot of them are believing that the Sagittarius arm and the outer arms are actually similar in brightness to the Scutum-Centaurus and Perseus arms. Now notice where our sun is. Our sun is in this section that here is labeled the Orion Spur. Nowadays, more researchers are often calling this simply the local arm. The local arm. In other words, there's some debate as to whether or not we're in a real legitimate arm or whether it's just a spur, and we're going to get back to that in just a bit. But the disk and bulge of our galaxy are embedded in what we consider to be a spherical halo of stars. So the bulge of the galaxy is basically just this central region, kind of imagine right at the center. And notice we also have a bar. We're going to have more to say about that bar soon. But the disk and bulge are embedded in a spherical halo of stars extending 50,000 light years from the galactic center. So by a halo, we mean the stars are very thinly distributed here. In that region that's not in the disk, the average distances between stars is much more than if you lie closer to the disk, like where our sun is. In the solar environment, the average distance between stars is something like 6 light years. But if you're in the halo, it's much greater than that. The disk itself is dominated by, well, basically 4 large spiral arms. The spiral arms contain hot, young stars. The bulge, on the other hand, contains almost entirely old, evolved giants, and so that appears yellow in color. The halo contains only old stars. So that should be kept in mind. Astronomers in the past have used this galaxy M83. It's sometimes called I think it's sometimes called the Southern Pinwheel Galaxy, as kind of a Milky Way look-alike. Thing is, M83 is a rather small galaxy. If I remember correctly, it's only something like 40 or 50,000 light years wide, compared with the Milky Way's 120,000 light years or so wide. So, again, we do live in a barred spiral galaxy. Here's a nice prototypical example of a barred spiral galaxy, NGC 1300, where the arms in this case are very tightly wound, and you have 2 major arms clearly emanating from the ends of the bars. In terms of a good Milky Way look-alike, this is my favorite one, UGC 12158. This is another nice barred spiral galaxy. You can see that there are a number of reasonably prominent arms and some other maybe not quite as bright arms going back here. And a lot of astronomers nowadays use this as an example of a good Milky Way look-alike galaxy. That's not the only one that people use. A lot of times when you see these cute little posters of galaxies that say "we are here," they're actually just taking some galaxy that really does not look like the Milky Way at all and just smacking a star in the middle of it and saying "we are here" and selling posters that way. Why don't they use ones like UGC 12158? One reason is that it's relatively far away, so we don't have as good in the way of high-resolution pictures of it. It's 384 million light years away. But nonetheless, it's similar in size and appearance and barness to the Milky Way galaxy. But there are a couple of others that astronomers sometimes use, ones that are a little smaller. For example, NGC 6744. This is about 30 million or 31 million light years away in the constellation Pavo. And notice that it has kind of something similar to our Large Magellanic Cloud over here, this orbiting galaxy that's getting disrupted and has lots of bright, young, hot stars that are forming as a result of that. So here is its central region, NGC 6744 that is, taken with the Hubble Space Telescope. You can here's kind of your bar right here, and you see these dust clouds, and you can also see a number of nice pink young star forming regions. Here's another Milky Way clone, NGC 3953. It's about 50 million light years away, I think 47 million light years away in the constellation Ursa Major. Now, what about this bar that you're seeing in these galaxies? What's the deal with the bar? Well, there's a cute little joke about this that at least comes to my mind. The bars of spiral galaxies are where all of the old, cool stars hang out. The young, hot stars are kicked out of the bar by gravitational interactions in this case. But the bar is an area where you have a bunch of stars that have gotten into a bit of an orbital resonance, and they all have similar, what we call coaxial elliptical orbits. So just kind of going back to here, the typical orbits of these stars are kind of big, ellipses, so maybe kind of coming out here and going over here, going back out, and then swinging in real fast, going back out, and similarly back over here. And this ends up creating a little bit of a gravitational resonance that helps to keep this action going. Bars don't last forever, I should mention, but it is something like 2/3 of spiral galaxies do have bars or bar-like structures. So they are more common than not if you're dealing with a spiral galaxy. But their origins are not 100% solved, but they do often serve as the beginnings of spiral arms in galaxies. And again, you're talking about stars in coaxial elliptical orbits. Here is an early image that kind of shows that our galaxy seems to have a bar. This is an image from the 2-mass survey, the 2-micron all-sky survey, and you see this kind of peanut-like region here. You're only going to get a peanut-like region here. We're talking about peanuts in their shell. If you have a situation where you have stars in pretty much coaxial elliptical orbits, which is exactly what we're talking about in the situation of a bar. So it's been confirmed Doppler profiles have shown that stars tend to travel on long, highly elliptical paths in these structures, and those paths tend to be basically the same. Our bar is about 28,000 light years from end to end. What other structure do we have? Well, we're also in a warped galaxy, if you're kind of feeling a little bit unbalanced lately. Well, due to mainly effects from our interactions with the large and small Magellanic Clouds with our galaxy's dark matter halo, that has kind of created some gravitational ripples traveling through that halo that end up kind of warping our shape. The warp is seen a little bit in this hydrogen map of our galaxy. And if you do kind of a best fit curve along this dotted line, you see that kind of warped structure. But more recently, we find that we actually look maybe a little bit more like this galaxy, ESO 510G13. That's where we actually have a visible warp. Here is kind of our latest artist's impression of what our galaxy would look like when viewed from the side far away. The green dots here are Cepheid variables. Remember, Cepheid variables, these are standard candles, so you can get distances to those with pretty high accuracy. In fact, the Gaia spacecraft has recently determined the distances to reasonably high precision to a number of Cepheid variables, which is why we've been able to, one of the reasons why we've been able to create a map like this over the past couple of years. So yeah, we definitely do live in a warped galaxy, and it probably has something to do with our gravitational interaction with the large and small Magellanic Clouds. In fact, there's the large Magellanic Cloud right there. Nice. And here is kind of a coordinate profile, so to speak, of the warp. If you imagine putting our galaxy on a plane and having that plane, that grid, go in the direction of the warp itself. Now, what about the interstellar medium? Our galaxy is composed of something like 400 billion stars, but remember, the size of a star is much, much smaller than the space between stars. That's why when galaxies collide, stars rarely, if ever, collide, because the only stars that will collide might be like stars in the centers of the galaxies, colliding either with each other or with stars from the other galaxy if you have a head-on collision. But generally, when galaxies collide, stars don't collide. What that means is that there's a lot of potentially empty space out there. Turns out that empty space is not all that empty. We find that it has quite a lot of neutral hydrogen, and that's something that radio astronomers can map, especially in the thin regions. So when neutral hydrogen gets sparse enough, a forbidden transition can occur, because what you can often have are just random flips of the electron from going from spin up to spin down, or vice versa. And when you have this flip going from spin up to spin down, this ends up emitting a photon. It's a very low energy photon. It has a wavelength of 21 centimeters. So we're talking about a very low energy type of situation. So this is something that astronomers can use, though, to help to map the Milky Way. Now, much of this gas layer is pretty thin, a good bit less than the thickness of the disk itself. Remember, the disk itself is about 1,000 light years or so thick, but the gas layer is more like about 400 light years thick. This is more kind of part of what we call the thin disk, but it extends beyond 80,000 light years from the center of the galaxy. And we also have hot X-ray emitting gas that extends in all directions, not just along the plane of the disk, for about 300,000 light years or so from the center. So the gas region goes way beyond where the stars go, because remember, the width of our galaxy is essentially 120,000 light years. Now, this hot gas halo has a mass equal to at least the mass of all the stars in the Milky Way. And don't forget, we also have a lot of normal gas in the Milky Way that makes up a lot of extra mass as well. But we're going to get to something else that makes up a lot more mass soon. But anyway, this is a map of the neutral hydrogen in our galaxy. That's what we mean by H1. H1 means when you have a 1 after an element, that means that that element's in its neutral state. If you had something like iron 3, that would mean that it's doubly ionized iron. In fact, in our sun, we have things like iron 23, means 22 times ionized iron, stuff like that. But anyway, so a typical spectrum for your neutral hydrogen, at least in terms of the amount versus the velocity, you find that, yeah, it's coming at us at different velocities in these areas where you look. And a lot of this has to do with the superposition of different regions along the line of sight. Now, the interstellar medium. So dust is also in what we call the thin layer of the galactic disk, or at least the thin disk. And this dust, again, tends to come from the remnants of exploded stars, which again tend to form in star-forming regions right in the middle of the disk, as well as normal stars like our sun shedding off their outer layers at the ends of their lives. Here is a very nice example of where you can see a lot of this dust in another spiral galaxy, one of my favorites, M104, the Sombrero Galaxy. This is an amazing spiral galaxy. It actually has one of the biggest known black holes at the center of any spiral galaxy. The black hole at the center of M104 has about 1 billion times the mass of our sun. In fact, based on the distance to M104 and the size of the black hole, that makes the M104 black hole one of the best near future candidates for the Event Horizon Telescope which is in the process of getting images around black holes for some galaxies like the Milky Way, M87, and a few others. Here's another nice edge-on spiral galaxy showing that dust very well, NGC 891. Now, as we mentioned before, the Milky Way has 4 major spiral arms, and our sun is near the inner edge of a short arm that you can either call it the Orion arm or the local arm, but there has been a bit of debate on that over recent years. We used to just call it the Orion spur, but some more recent research seems to indicate that this is actually more of an arm offshoot that's a bit longer than expected coming from the Sagittarius arm. So there's a bit of pride at stake here, you know. I mean, we'd much rather live in a real legitimate spiral arm instead of just living in a spur. Anyway, the rotation of our galaxy is such that it takes about 240 million light years, 240 million years for our sun to orbit the galaxy once. So consider it this way. If that 240 million years is right, the actual estimate is somewhere between like 220 million years and 250 million years, something like that. But if you take that 240 million years at face value, consider this. 230 million years ago was when the dinosaurs first arose on the planet, having evolved from pre-dinosaur reptilian animals. Well, the dinosaurs, of course, went extinct 66 million years ago, so the last time that our sun was here in this part of the galaxy was before the dinosaurs had evolved. That's pretty cool, I think. So, in the outer parts, the Milky Way does not rotate as what one would call a solid body, but as you get closer to the center, it's more what you call solid body rotation. The reason for that is that as you go outward from the center, there's more and more mass in an imaginary sphere centered on the center of the galaxy and going out toward where you are. And whenever you have a uniform density region like that, the result is going to be solid body rotation, meaning that all parts of it will rotate at the same rate. In other words, the same number of revolutions per gigayear or something like that. But as you get farther from the center, you don't have that uniform density holding up. So generally, in that case, you would expect the rotation rate to fall off. We're going to come back to this because this has some enormous implications, not just for our galaxy, but for the universe as a whole. Now, how do we get spiral arms? When people started first thinking about this, they considered the situation of maybe as our galaxy formed and started rotating, you ended up kind of tracing out spiral arms due to this continued rotation with this gas and dust and stars. Well, that turns out to be a problem because, again, in the case of our sun, it takes about 240 million years to go around once. Let's just round that to 250 million years. And our galaxy has been around for probably like 12 billion years. Let's just round that down to 10 billion years. So 250 million years into 10 billion years, well, there are 40 quarters and $10, which means that we've gone around about 40 times. The galaxy has gone around about 40 times in our sun's region since our galaxy formed. Well, that should mean you should have lots and lots of winding. This should be wound up really, 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 really tight. Lots and lots of spiral arms, or at least they'd all be, apparently, the spiral arms themselves will be right next to each other. Instead, we have 4 distinct spiral arms. This is called the winding problem. And this shows that this whole idea of the spiral arms just being due to rotation after the formation of our galaxy is not how our spiral arms came to be. Instead, the spiral arms themselves, we realize, are simply regions where material temporarily bunches together. So I should mention that observations have revealed that not just for our galaxy, but spiral galaxies in general, spiral arms rotate more slowly than the stars and the gas and the dust. Thus we say that the stars, gas, and dust are leading the spiral arms. Now, every once in a while you'll come across a weird galaxy where that's not the case. In fact, I'm thinking of one in particular where one of the spiral arms is leading the stars, gas, and dust, but the others are not. And that galaxy looks like something funny's going on there. But anyway, in most spiral galaxies, the stars, gas, and dust lead the spiral arms. But due to gravitational pull of material, the stars spend slightly more time in the arms than they do elsewhere. In other words, they get kind of pulled toward the arms somewhat, and then they're kind of held there by the collective gravity of everything there, and then they eventually kind of moved out. Well, as that happens, as these clouds of gas and dust enter the spiral arms, they collide with the gas and dust that's already in the spiral arm, and that triggers star formation. And surprise, surprise, the spiral arms are where your bright blue massive stars are. These are kind of signatures of your star-forming regions. Look at all these star-forming regions, all of these pink nebula regions. These are giant molecular clouds. The Whirlpool Galaxy is a great example of a situation where you have a very nice burst of star formation as the gas and dust enters the spiral arms. Now, we'll have more to say about spiral arms when we get into talking about other galaxies, but I'll just say that, long story short, the reason they occur is because, at least the reason we think they occur, is because you have essentially a density wave that occurred in the center of the galaxy due to some interaction there, and that density wave propagates outward in all directions. And as that density wave hits gas and dust that is going around at different rates, you end up getting triggers of bursts of star formation. But since that density wave is propagating outward while the galaxy is rotating, and the inner parts go around faster than the outer parts, at least in terms of angular frequency, that means that you're going to get a spiral structure when that happens. And then once you start getting that kind of keeps the pattern going. That's an overdense region, which ends up kind of being a self-sustaining type of thing. Now, again, we're going to talk more about this when we talk about galaxies in a different lecture. Where are the stellar populations in our galaxy? Well, population 1 stars, remember those are the younger stars, the ones that have more metals in their atmospheres. Remember, metals are anything heavier than hydrogen and helium. Population 1 stars are found only in the disk, and they're primarily in the spiral arms. When I say primarily in the spiral arms, like, yeah, there are a few of them that are in the bulge, kind of around the center of the disk, so to speak, but not very many. And you have lots of young, hot O and B stars in open clusters in the spiral arms. That really helps to make the spiral arms more pronounced. On the other hand, population 2 stars are anywhere they want to be in the galaxy. They're in the disk, they're especially in the bulge, they're in the bar, and they're in the halo surrounding the galaxy. There are no population 1 stars in our galactic halo for a very simple reason. Population 1 stars, generally speaking, would have been younger, probably more massive, and in order to get into the halo, well, that's a longer orbit. A lot of those would have exploded by now. Population 2 stars include stars in globular clusters. The globular clusters, if you remember the map that Harlow Shapley made, they're roughly spherically symmetric about the center of the galaxy. That's how Harlow Shapley concluded that our sun is not in the center of the galaxy, because the globular clusters are not spherically symmetric about us. They're spherically symmetric about something else. Population 2 stars are also just about the only types of stars in the bulge, and they're the only types in the halos. Now, very close to the center of our galaxy, you do have a burst of star formation where you have a lot of population 1 stars, but those do not make up the large majority of the stars in the bulge. So population 1 stars, they're mostly young, and remember, they're forming today. Our sun is a population 1 star, and population 2 stars tend to be very old, often 10 to 13 billion years old, and they have low amounts of metals. They were the first stars born in our galaxy. But again, in the spiral arms, nearly all the stars are actually population 1 stars, like our sun. Now, based on where our sun is in the galaxy, and how long it takes to go around, we can use Newton's version of Kepler's third law to measure the mass of the Milky Way. Isn't it delightful? So, remember, the way that we thought of it before was, well, Kepler's version was that period squared of a planet is proportional to its semi-major axis cubed going around the sun. Now, turn that proportionality into an equality by comparing things with Earth. You get that period squared in years is semi-major axis cubed in astronomical units. Kepler had no idea why. He just noted it was an observational fact. It was a law of nature. Isaac Newton showed us why. He started off with universal gravitation, law of universal gravitation, and he was able to derive Kepler's third law. But Newton's version is a lot more meaningful, because now you can actually plug in any numbers you want and going around any object you want, as long as things are in consistent units. So what Newton got was that t squared equals 4 pi squared a cubed over gm, where m is the total mass of everything involved. Well, let's be a little bit more precise here. The total mass is actually going to be the total mass that is interior to your orbit. Newton showed that it's mass that's interior to an orbit that affects the orbit. Mass that's exterior to the orbit does not affect the overall scope of the orbit. Yeah, it might tug one way or the other if there's, say, some funky mass distribution or something like that, but overall, it's not going to change the orbital period. So anyway, take Newton's version of Kepler's third and turn it into a ratio. In other words, compare it with the sun. We know, and Earth going around the sun. We know that Earth takes 1 year to go around a star that has a mass of 1 solar mass. So setting up that ratio, you can get rid of this 4 pi squared over g. These are just numbers. And you realize that after you've rearranged it into this form and reduced, the mass of our galaxy, at least interior to our sun's orbit, in solar mass units, is equal to the semi-major axis cubed of our orbit in astronomical units divided by the period squared of our orbit in years. And when you plug in the numbers for our sun going around the center of the galaxy, you get about 100 billion solar masses. In fact, I think last time I plugged these numbers in, I got something like 86 or 88 billion solar masses. But, I mean, you can round that to, again, this is an approximation in any case. Because our sun's orbit around the galaxy is not perfectly circular. So we realize that the mass interior to our sun's orbit is about 100 billion solar masses. Now, based on that, it is possible to do this with other stars, because using the Doppler method, or at least using spectroscopy and figuring out the speeds of the stars going around our galaxy, we can figure out how much mass is interior to their orbits as well. The result ends up being quite unexpected. This was discovered starting, I believe, in the 1970s. Vera Rubin became really famous for all of her work in this effort, not just with the Milky Way, but also with other galaxies. And when you make a plot of the orbital speed versus distance from the center of the galaxy, things first start off being pretty much what you'd expect. Here's that straight line going up. That's that solid body rotation that we were talking about when you're close to the center. And then as you kind of get outside of the bar, you have this kind of funny wavy pattern. This is all what you would expect given the actual known mass distribution of our galaxy. But then, once you get out to about 35,000 light years or so, you would expect that the rotation curve, as this is called when you plot orbital speed versus distance from the center of the galaxy, you would expect that would start to fall off. Because as you get farther and farther from the center, you're not dealing with lots and lots of extra stars or anything like that. But instead, what the data shows a leveling off, in fact, actually a rise after a certain point. That's really weird. And that rise continues when you plot not stars, but clouds of gas. You realize that there's a lot of unaccounted mass in our galaxy. And we are able to keep track of what we can see, but based on the motions of distant globular clusters, we realize that the total mass of our Milky Way is about 1.5 trillion solar masses. And we realize that that mass is not made of things like stars or gas or dust, because we can see that stuff. So because we can't see this extra mass, we call it dark matter. In short, we don't know what composes dark matter, but we know that it's not something that has ever been created in a laboratory. It's not something that we've ever directly studied in a telescope either. Instead, it's something completely new. It could be some supersymmetric particle that comes out of things like superstring theories and stuff like that, although the belief in that is starting to wane, as we should have detected such a particle at this point in the Large Hadron Collider, if the simpler versions of these supersymmetry theories were correct, and yet we have not. That is turning a lot of people away from supersymmetry ideas at this point, although there still becomes a problem because we don't have any better ideas of how to unify the forces of nature. That's something we'll get to when we talk about cosmology. But in any case, we realize that this dark matter, which we now recognize makes up the great majority of mass, not just of our galaxy, but the great majority of the mass of the universe. In the case of the Milky Way, we have a dark matter halo that's about 900,000 light years wide. And the Andromeda Galaxy's dark matter halo is even bigger, extending over halfway its distance to our galaxy. The Andromeda Galaxy is something like 2.4 million light years away, so that means its dark matter halo is over 2.4 million light years wide, given that extending over halfway from the Andromeda Galaxy to the Milky Way would mean that its radius is over 120,000 over 1.2 million light years. So the overall diameter is over 2.4 million light years wide. Here is an artist's reconstruction of our Milky Way amidst the dark matter halo colored in blue. Now, all this other stuff that you see are the dwarf galaxies that orbit the Milky Way. A lot of these dwarf galaxies are real, but there are others that are still probably awaiting discovery. And we're going to have a little bit more to say about those relatively soon. So, based on lots of studies that have been undergone, not just with our galaxy, but also with other galaxies, clusters of galaxies, and the universe as a whole, we now recognize that dark matter makes up about 25% of the mass energy in the universe. Dark energy makes up about 75% of the mass energy of the universe, which means that the rest, which is 5%, is what makes up everything else. In other words, the typical solid, liquid, gas, plasma states of ordinary matter, that makes up only 5% of the mass energy of the entire universe. Now, due to our extensive dark matter halo, that gives the Milky Way more mass power, so to speak, to shred other galaxies. And studying the remnants of these interactions between the Milky Way and other galaxies in the past has revealed a number of star streams that can be seen in the sky using, in this case, Palomar survey. The Sagittarius stream is the stream coming from the Sagittarius dwarf galaxy, which is a galaxy that the Milky Way is in the process of eating up. We're going to come back to that soon. As we mentioned before, our galaxy has a central supermassive black hole. That black hole has a mass of 4.5 million times the mass of the Sun. We know that it's in a very small region because we're able to watch stars orbit it. And some of these stars are getting as close to the central object as something like 120 astronomical units. And that tells us that you're dealing with 4.5 million times the mass of our Sun in a region that's about twice the size of Pluto's orbit. Okay, 3 times the size of Pluto's orbit. Well, that only makes sense if it's a black hole. If that's not a black hole, it's something even more exotic and surprising than a black hole. So there's nothing that is visible there, but there's 4.5 million solar masses there. We do believe that pretty much every massive galaxy has a supermassive black hole in its core. In fact, the Milky Way supermassive black hole is rather small as galactic black holes go. In fact, there are even dwarf galaxies that we know of that have bigger black holes than what we have. We should feel bad. But in any case, it's known that these supermassive black holes form quite early in the lives of galaxies. In fact, recent images from the Hubble Space Telescope have been showing us that there are galaxies that are only about 1 billion years old. In other words, these are really, really distant galaxies that are about, say, like 12 billion light years away or so, which means that we're seeing that light as it was emitted only 1 billion or so years after the Big Bang. That these galaxies are seemingly mature galaxies that already have really large black holes. These black holes can influence the behavior of their host galaxies in a number of ways that we're going to explore when we talk about galaxies in general. Now, in addition to our black hole at the center, we also have a whole bunch of satellite galaxies. The 2 most famous are the Large and Small Magellanic Clouds. We also have the Sagittarius dwarf galaxy that I just mentioned. The Milky Way is in the process of gobbling that thing up. And in addition to that, we have at least 59 other galaxies as of my last check. So as of May 2020, the Milky Way has about 60 dwarf galaxies, or 60 galaxies orbiting around it. In fact, it is believed that pretty much any large galaxy is going to have a number of these little dwarf galaxies orbiting around it until it consumes them. So, again, a lot of these things are in the process of interacting with the Milky Way. In the case of the Sagittarius dwarf galaxy, the history of that interaction has been unveiled by a series of studies particularly conducted by Steve Majewski and Mike Skrutsky at UVA and their associated teams of colleagues and graduate students. So, this is a picture of the globular cluster M54. We consider it one of the Milky Way's globular clusters, but that's a lie. M54 is actually a globular cluster that we have stolen from the Sagittarius dwarf galaxy. We are taking it over in the process of consuming the Sagittarius dwarf galaxy. So here is kind of an older map showing some of the known galaxies that orbit the Milky Way. And again, these are basically all dwarf galaxies. And the Andromeda Galaxy also has some galaxies orbiting it as well. But this obviously doesn't show all of them because, I mean, nowadays we know of like 60 of these things. But it still shows a number of them. And you can see that they're in a number of different areas on this map as well. So we are a very exciting environment. Lots of dwarf galaxies orbiting around the Milky Way. Some of these dwarf galaxies only have on the order of like a few thousand stars or so. In other words, a lot of globular clusters have a lot more stars than these things have. But some of these things also have a whole lot of dark matter. Not all of them, though. We have found a couple that seem to be relatively lacking in dark matter. But some of these dwarf galaxies apparently have a lot of dark matter. So here is our parting shot of the Milky Way lookalike, this UGC 12158 galaxy that's about 384 million light years away. And again, a very nice spiral galaxy that gives us some insight into what a galaxy like our Milky Way is actually like. So hope you'll join me next time when we talk about other galaxies as well. Thank you.